Now we look at the next sequential logic storage device, which is the D Latch. Okay? So reminding ourselves where we've been, we have our flow here of where we've been and where we're trying to get to. So we started with the cross-coupled inverter pair, looked at the SR latch, the S bar R bar latch, the SR latch with enable, and finally we are at the D latch, and this becomes a device which becomes very useful, and ultimately it'll lead into the D flip-flop, which we're trying to go to. Okay, so to understand the D latch, let's look at the SR latch with enable one more time and take a look at its truth table and see what we want out of it and what we don't want out of it. So notice this. We have this nice behavior. We can store based on C. We can put it into a mode where we can set and reset based on S and R when we set C to a 1. However, we have these two don't use states. And notice what they are. Notice that whenever S and R are the same thing, we don't want to use the state. So when they're both 0 and 0 or they're both 1 and 1, we don't want to use it. But we do like the states where they're the opposite of each other. So it turns out that what we can do is we can manually change, or we can manually force S and R to be opposite of each other by putting an inverter on S. So S will come in and go through an inverter, and then we'll eliminate the R signal altogether, and that will allow this truth table to be condensed, and that then becomes the the D latch. So let's take a look at the circuit here. So this is the circuit for a D latch. What we do is we took S was up here and R, we got rid of it. So we take S and it comes in and we put an inverter, and that will force the S and the R to always be opposite of each other. Since we've now eliminated S and R, we've come up with a new signal name, input variable, and it's going to be called D. Okay, and this becomes the new symbol for the D latch. So we stop drawing all the gates anymore, and we put it as kind of a building block. So we've got D and C, Q and Q bar. So the output's Q and Q bar. C is the reason we call it C is for clock, and D now stands for data. We can reduce the behavior model here in the truth table even further by doing this. Notice that when I have a 0 on C, it'll store, and that's how the SR latch with enable worked. But notice that when I have C is equal to 1, I'm going to take D, and if D was a 0, let's think about what's happening. D was a 0, where that puts a 0 right here and a 1 right there. Okay. Well, that is the reset state for the SR latch with enable. So it drove the Q to a 0, and it drove Q bar to a 1. Okay, well that's fine. Let's take a look at now when I had a 1 on D. Okay, so this situation now, I'm going to come in here, and I'm going to have a 1 right here on D, and which used to be S, and this is now going to be a 0. Well, that is the set state for the SR latch, or the SR latch with enable. So it takes Q to a 1. But more importantly, look at what's happening with the outputs and D. Q is always tracking what D is. So when you're in the normal operation mode, which is C is equal to a 1, if D is a 0, Q is a 0. If D is a 1, Q is a 1. And of course, Q naught is always acting the opposite, the way it should. So we actually have this state which we call the track state. So the output is simply going to track whatever D is, and then if you ever move from the track state into the store state where C is equal to a 0, then what's going to happen is it's just going to grab it, or what we say latch it, and you will store that information. So that's how a D latch works. So here's a timing diagram, and let's walk through it from left to right and see how it works. So I'll block off some of it so we go through step by step in time increments. Okay. So first of all, actually, it'd be useful to keep this table on the screen too. Yeah, that'll be very helpful. Okay, so we are going to start off where D is a 0 and C is a 0. So C is in the last state. Okay, so now let's put Q is at a 0 and Q bar is a 1. Okay. Okay, so now we go into the C goes to a 1. We move into the track state. Notice that whatever D does, in this case it just went up, down, up, Q will track it. So it's just going to match it. But then look at this situation right here where C went to a 0. It went from the track state to the hold state, or store state. So it was in track and it went to store. But D happened to be at a 1 at that time. That means Q is going to lock in a 1 and latch it, and it will hold it for the entire time that C is a 0. And it didn't matter if D changed states in there. It doesn't matter because it's in the hold state. So it ignored that transition. So then when I go back and I say, okay, now what happens when I go into the track state, or track mode, where C goes into a high, then it goes back to holding it. Well, notice that when it went into track right here, D was a 0, so it was holding a 1 right here. It had to pop down to a 0, and now it's going to track. And in that example, all it did was just stay at a 0, and then from then on out. So this is now the D latch, and this gives us a powerful device because we can use this, we'll call it the clock, and what we can do is we can track and hold information based upon 2 signals. So we can have data coming in, and we can track it and let the output match it, and then when we want to store, we just take the clock signal to the other state, go into the track mode, and it'll hold whatever D was at that moment. So this is the D latch.